Okay, so let us start. So sorry, there was some issue with the WhatsApp in sharing the really link. So I reshare it just now, and so good to know, good to see that all of you are, most of you are able to see it and join it. So since people are keep on joining, yeah, let's wait for a couple of minutes and see if somebody who is coming or not. But anyway, I will start writing things so that people will start joining. Okay, so last time what we talk about certain properties of sequences, especially about the convergence of the sequences, right? So we see that there is a theorem called Sandwich theorem, which helps us to verify whether a sequence is converging by using the fact that we can we have known the convergence of some standard sequences, something like 1 upon n or 1 upon a to the power n, something like that. So we will move on and let's do a couple of exercises. First, sorry. Okay, so this exercise is about the relationship between a limit and certain values, right? So it says that if the sequence has a non-zero limit, then after certain n, all the components of the sequence should be non-zero. Then only the sequence will have a non-zero limit, right? So let us show this. Okay, so let us take L be the limit of the sequence, right? And it says the limit is non-zero. So you clearly know L is a non-zero number, right? So L is non-zero, you know, because sequence has a limit and that limit is non-zero. Now, because L is non-zero, you know that by the property of absolute value, which you studied earlier, you know that absolute value of L is strictly bigger than 0, right? Absolute value of L is strictly bigger than 0, you know that, right? So if that is 0, then you know that by the in the definition of the limit, you can choose epsilon as absolute value of L, right? And because the definition says for every epsilon positive, and you know absolute value of L is positive, so you can take that as epsilon, right? So then you know that there exists n belongs to natural number such that xn minus L is less than absolute value of L for all n bigger than n. Okay, so you know that this is because of the definition of the limit, and you choose epsilon as L, right? So that is only thing you did. But by absolute value, you have this relationship. Okay, so because you studied this with the properties of absolute as a consequence of triangle inequality, that absolute value of xn minus absolute value of L, the absolute value of that quantity is less or equal to xn minus L. Right? So this gives us something that xn belongs to natural number such that actually minus absolute value of L is less or equal to xn minus absolute value of L less or equal to absolute value of L for all n bigger than n, right? So because this one is less than this, but this is less than absolute value of L, so this quantity is less than absolute value of L, right? Not less or equal, less than. Strictly less than absolute value of L, and then you remove this absolute value, so you get minus less than quantity less than plus of that value. Okay, so this says if you take this part, right, and add L on both sides, absolute value of L on both sides, right? So you get this. There x is n belongs to natural number such that 0 is strictly less than absolute value of n for all n bigger than n, right? So what you get is when you take only that part of the inequality, you get 0 less than absolute value of xn for all n greater than n, right? For some n. Okay. It's I hope we had some issues with the power, but I think all of you are okay. So let me continue. Okay, so this is what you have. 0 or x absolute value of xn bigger than 0. If absolute value of xn is bigger than 0, then that clearly shows you xn is not equal to 0 for all n bigger than n. And so that's how you show that if the sequence has a non-zero limit, then at least at the tail, right, the sequence will be non-zero for all n, right, and at least around the tail. Okay. Now let us write down a couple of exercises, but I will leave the proof as a homework. Okay, so these are again showing the limit of a certain sequence is equal to 0, right? So they ask you to show that if a is between 0 and 1, a to the power n will converge to 0, right? And also if p is greater than 0, then 1 upon n to the power p will also convert to 0, right? So I will give you a hint. Okay, so the hint is this: you try to get x as a 1 upon a minus 1, because a is between 0 and 1, so 1 upon a is bigger than 1. So 1 upon a minus 1, that is 0, bigger than 0, right? So what you do is you try to write 1 plus x to the power n's expansion, right? And then by using this relationship, you should be able to get a relationship like this. And then according to sandwich theorem, you can say that 1 upon a to the power n will be going to 0 as a goes to infinity. That is for the first part. For the second part, you pick x as n minus 1. Okay, and then sorry, px. Okay, so you choose x as n minus 1, right? And then so clearly x is greater than 0, that is understandable, right? So you know that. And then again you write the binomial expansion. You studied in A level the binomial expansion, right? So 1 plus x to the power p, and once you write that, you try to get an inequality like this: 0 less than 1 upon n to the power p is less than 1 upon px, but you know x is n minus 1, so that's positive. So as n goes to infinity, x goes to 1 upon px goes to 0. So then by sandwich theorem, you can see that actually the limit of the sequence will be 0, right? So these are again application of sandwich theorem, but in a different way, right? So you apply that in a different way. And before I move on, let me write down a couple of more exercises for you as the homework, and then I will move on to the next section, which is about the criteria for convergence. Okay, so these two I leave as an exercise, because this is again, you try to, the first part you try to prove the limit, existence and convergence, right? So you can use the theories which we studied earlier, the Sandwich theorem or other convergence theorems, right? To show that this one, the sequence of the limit is 0 for the first one, and also the limit will be 0 for the second one. So you can see that this one is about, these two relationships are about the relationship between two successive terms, right? So this is xn plus 1. Actually, if you simplify this inequality, it says xn plus 1 is less than xn. So that means the sequence is decreasing, right? Xn is bigger, xn plus 1 is smaller, xn plus 2 is even smaller. So it's basically a decreasing sequence, right? And they are positive sequence, so they, all the values are bigger than or equal to 0, right? So in that case, you see that the sequence goes to 0 if it exists, right? So this one also, this is actually the ratio between the two terms, may depend on n, but that actually, that limit actually goes to that limit is actually less than 1. So in that case, the sequence is converge, right? So then these two, you can find the limits of these sequences in different other ways also. You can apply Sandwich theorem and other things, but here I put this again because you can try using these two results, one or two, right? One of those two results to find the limit, right? So you can take the ratio, and if the ratio is less than 1, then you can say that goes to 0, or you can take the ratio and the ratio depends on n, then you apply the limit or take the limit of the ratio, and if that value is less than 1, then you can say the limit is 0, right? So actually this one, first one can be find by using this results, and second one can be found by using this, right? So these are exercises. I leave it for you to do as a homework in order to understand what we have studied so far, right, about limits and other convergent properties. Now what we are going to do is we are going to talk about another type of sequences. Actually it is somewhat related to this kind of a relationship. So here you can see that the sequence is decreasing, right? In a sense, we can say it is decreasing. Similarly, you may have sequence that may be increasing, right? So let us define how, let us write down the definition for increasing and decreasing sequences, and then we talk about how we can find the limit of decreasing or increasing sequences in a different manner, right? So in general, sequence that are increasing, decreasing, right, they are called monotone sequences. Okay, so this is how you already know that by the name itself, you know that increasing means the successive values keep getting bigger and bigger, right? So xn plus 1 will be obviously bigger than xn, and decreasing means xn plus 1 will obviously be smaller than xn, right? So smaller or equal in this case, right? So when we have strict inequality, we say strictly increasing or strictly decreasing, right? So you can see a few examples as well, right? So 1 upon n is actually a decreasing sequence, actually strictly decreasing sequence, right? So these are kind of obvious for you as of now, right? Because you have seen enough of these. right? So in this example, you can see that the sequence will be actually like this: 1, 1, 2, 2, 3, 3, like that. So in this case, it is increasing. Right, so these are few of the examples for increasing sequence or decreasing sequence. The fourth one is actually xn is equal to 1 upon n, n or 2 upon n, even and 2 upon n plus 1 with n odd, right? So this is actually, you can easily figure out these things, right, by just looking at the few terms of the sequences, right? You can say that whether the sequence is strictly increasing or strictly decreasing or increasing or decreasing, right? So in general, so this is a general term, right? Monotonic, we call it monotonic if it is either increasing or decreasing, right? Any kind of increasing or any kind of decreasing, maybe strictly increasing, maybe strictly decreasing, right? Just increasing or just decreasing, right? So combination of all kind of this relationships, right? Increasing, decreasing relationships, those kind of sequences are called monotonic sequences, or right, actually these sequences are said to be monotonic, right? If someone say let xn be a monotonic sequence, then you should understand that whether it might be increasing or decreasing, right? So one of them, one of that should be there. It might be increasing or it might be decreasing. So this monotonic relationship can also be used to determine the convergence of a sequence, right? So that criteria is called monotonic convergence theorem. Let me write down the theorem first. Right, so this monotonic convergence theorem, right, also known as monotone convergence, right, or let me write down monotone. And so monotone convergence or monotonic criterion, right? So this says about convergence of a monotone sequence. This theorem is very simple, right? So it's simple to state, right? It says every monotone sequence that is bounded is convergent, right? So let me write down for increasing sequence first. Right? So every increasing sequence that is bounded above is convergent. That is the monotone convergence theorem, right? So you can see that in the picture as well, right? So So you may have a sequence like this, increasing, 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 increasing like this, right? So if there is no bound, it will keep on going like this, right? Increasing sequence. If there is no bound, then it will keep on increasing like this, right? So you can see that. If you have an increasing sequence, let me draw it in green. Right? So if there is no bound, it will keep on going like this, right? But if I say there is a bound here, right? And then if the sequence is bounded above, then it cannot cross the upper bound. So anyway, it is increasing, but it should stay below the bound, right? Upper bound. So the only way is it will go very close to the upper bound, right? So after certain point, the sequence, the tail of the sequence will get very close to the upper bound, right? Or it will go inside the little tube around the upper bound, right? So that is what the monotone convergence theorem is about, right? So if the sequence is increasing and bounded above, then we say that it is bound, it is convergent. And similarly, the other way around is also true, right? Decreasing sequence that is bounded below is also convergent, right? So we will try to prove this, right? So it is not a big proof, but we will use some results which we already studied earlier, right? Something like a completeness property and stuff like that. So let me start the proof, and if I can finish, I'll finish it today. Otherwise, I will go to the next class. Right. So let me take a set. Right. So proof. You know, xn is increasing, comma bounded above. Okay, so you have a sequence xn that is increasing and bounded above, right? So you need to show that it has a limit. So let me define a set of all xn such that n belongs to natural number, right? So let us take the set of all values in the sequence, right? Sorry. So then right, so S is non-empty clearly because it contains the values of the sequences, so obviously it is non-empty, and it is a subset of real number. That is understandable, right? Because all the components are real values, and also because the sequence is bounded above, the set is also bounded above, right? So then it comes down to completeness property, right? So by completeness property, you know that supremum of x s exists, right? Now you take L be the supremum, right? L be the supremum. If L is the supremum, then what can you say, right? So 1 xn is less or equal to L for all n belongs to natural number, because every element in the set should be less or equal to supremum. And second one, right? There exists n, actually there exists xn belongs to S such that L minus epsilon is less than xn, right? You know that if, right, also for epsilon positive, by the definition of supremum, you see that xn is less or equal to L for all L. At the same time, there exists some xn in the set S such that if you go epsilon below the L, then you get an xn bigger than that. So eventually, these two combines what? Their exists belongs to natural number such that, right, L minus epsilon less than xn less than or equal to L, which is obviously less than L plus epsilon. You know that. Right, so what you have is, you have there exists n belongs to natural number, or leave it like that. So let's say this. First we will see this, right? So for some epsilon positive, there exists a natural number n such that L minus epsilon is less than xn, right? Okay. But it was given that xn is an increasing sequence. Because xn is an increasing sequence, you know that because xn is an increasing sequence, for every n bigger than n, right, xn is capital N is less or equal to, right, xn for all n bigger than n, right? Xn is less or equal to xn for all n bigger than n. So now you combine this and this, right, and this, right? So actually there exists n belongs to natural number such that you have L minus epsilon less than xn, but that is less or equal to xn, but xn is less than L equal to L, which is less than L plus epsilon for all n bigger than n, right? So if you combine this and this together, you get L minus epsilon is less than xn is less or equal to n. So this says there exists n belongs to natural number such that L minus epsilon is less than xn is less than L plus epsilon for all n bigger than n. So what you have, for every epsilon positive, there exists n belongs to natural number such that absolute value of xn minus L is less than epsilon for all n bigger than n. So that is what we have, the definition for the limit, right? So this says limit of xn n goes to infinity is actually n. Okay. So what we did is, we take the set of components of the sequence, and because of boundedness, we apply the completeness property and get the supremum, right? And then we show that the supremum is actually the limit. In order to show that supremum is the limit, we apply the properties of supremum or definition of supremum, and also use the facts that xn is an increasing sequence, right? Combining all of them, we get the required relationship. And similarly, you can prove the monotonically decreasing sequence that is bounded below will also have a limit, right? So I will stop here, and I will continue tomorrow again with the other properties of monotonic sequences and how to prove the convergence. Right. So I will stop here and then continue tomorrow.